Take the differential equation f prime of x equals f of x plus 1, which can be equivalently written as dy over dx equals y plus 1. When we solve for y, we're trying to find the function, or set of functions, whose slope at any given point is equal to the value of the function at that point plus 1. Here's a method that you might see people use to solve this kind of problem. Multiply both sides by dx, and divide by y plus 1 to separate out the x's and y's. Then take the integral of both sides, which gets rid of the dx's and dy's. And finally, we can solve for y in terms of x. In this case, c is just a constant, and our claim is that this function will be a valid solution for any value of c. Going back and checking what we got with our original differential equation, we find that this function does indeed work. However, to a first-year calculus student like myself, what we just did might at first seem to be completely unreasonable and a blatant abuse of notation. dy over dx is supposed to represent the slope of the function. You can't just treat it as a fraction and separate them like that. And how about this step where we integrate both sides? The two integrals aren't even with respect to the same variable. Surely that can't be allowed. The purpose of this video is to attempt to justify both of these moves visually, and hopefully make it a little bit clearer what exactly it is we're doing when we solve these kinds of problems. Let's say this is a function that satisfies our differential equation. We have our dy and dx, and the ratio of these two numbers is our slope. One thing to note is that dy and dx are normally supposed to be infinitely small, or more precisely, we're supposed to take the limit as dx approaches 0. They're enlarged in this diagram so you can see them. But what's important to keep in mind is that the arguments we're about to make hold true for any arbitrarily small value of dx or dy. Knowing that, what we notice from this diagram is that dy and dx don't necessarily have to be bound together for our equation to make sense. It's just stating a relationship between dx, dy, x, and y for points on the function, which is that the length of dy divided by the length of dx is always equal to the y value at that point plus 1. When we rearrange our equation, what it's saying is that for any point on the function, dy times 1 over y plus 1 will always equal the dx at that point. Now, in order to take this information we have about these tiny changes in x and y and extract the explicit function, it's common to say that we can just integrate to add up all of the dx's and dy's. But what does that actually mean? To aid in visualization, let's replace this indefinite integral with a definite integral. We know that each dx is equal to 1 over y plus 1 times each dy. So from some point on the function x1, y1 to another point on the function x2, y2, the sum of all dx's on this interval is equal to the sum of all dy's, each multiplied by their corresponding 1 over y plus 1. To make it clear that what we're doing here is integration, we could even visualize this sum of products as the area underneath the curve 1 over y plus 1 from y1 to y2. You'll notice that the area of each rectangle is equal to dy times the corresponding 1 over y plus 1. The sum of these rectangles, the total area, is what we want to find. Evaluating our two definite integrals, we find that for any 2 points on the function, the change in x is equal to the change in the value of ln absolute value y plus 1. In other words, if we're at a point on the function and we increase x by 2, then y must increase by an amount such that the natural log of y plus 1 also increases by 2. On our function, the value of x and the value of ln y plus 1 increase and decrease together, and therefore, we can say that ln y plus 1 is just equal to x shifted up or down by some constant c. So that's it. We've done it. We've shown why these two key steps in solving separable differential equations, separating out the variables and integrating both sides, make sense. and we've uncovered a deeper geometric meaning behind the process.